Thank you very much, Troy. If you ever get tired of quantum chemistry, I think you could be a talk show host. Just beautifully done, but of course made easier by the sort of amazing young hires that we have. You've heard Lincoln Labs referenced multiple times today. And one of the things that's an important part of my role is oversight over the lab. And they do remarkable work every day in the national interest, and they have a very significant effort in quantum. And Dan Rippon is here to sort of talk about some of the work there with you today. He's the head of the Advanced Technology Division. He's co-lead also of their Civil Space Systems and Technology Office. He leads research and development across a wide range of technologies, enabling new national security capabilities. He has efforts in microelectronics, microsystems, imagers, lasers, radio frequency systems, photonics, and quantum. He's an MIT alum, having earned his physics PhD in research on ultrafast lasers and photonic crystals. So please join me in welcoming Dan.
Thanks, Ian. It's an absolute pleasure to be here today representing MIT Lincoln Laboratory. We're very thrilled to be part of the MIT Quantum Initiative, and it was very fun walking in this morning across the street from Building 36, where I did my graduate work in the Research Lab for Electronics. So very nice to come back here. If you'll go to the next chart. Oh, sorry, how do I advance the charts? Yeah. Okay, thanks. So I just wanted to introduce everyone a little bit in case you don't know about who MIT Lincoln Laboratory is. We're an MIT laboratory, about 4,500 people out in Lexington on Hanscom Air Force Base. And we really have a focus on doing work developing technology for national security applications. We really focus on looking at the architecture of possible technological solutions, developing some of the long-term research and development that will enable some of those capabilities, and then ideally very quickly prototyping those capabilities and getting them out to the field to have an impact, and also to industry where those things can really scale and have a much larger national impact. Lincoln was, our roots, our ties back to MIT really go from our beginnings. As Ian, I think, mentioned earlier in the day, we were started in 1951, and we really grew, like RLE, out of the MIT Radiation Lab. The nation had a challenge in terms of the threat of Soviet bombers coming over the North Pole, and we really didn't have a sensing system or architecture that could be used to protect us from that potential threat. This, I think, is a great example of not only the collaboration between MIT campus and Lincoln Laboratory, but shows how we worked from architecting the overall the solution, developing some of the enabling technologies such as real-time computing and magnetic core memory that really enabled some of those applications, and then ultimately transferred that technology by spinning off MITRE to really acquire that system for the country. And after that, we've really gone on over the past 75 years to expand our national impact, not just in air defense, but in areas like missile defense, space surveillance, radar, radar imaging of satellites, and core enabling technologies. I'd like to just highlight a couple of these on the bottom right. One is Lincoln Laboratory really did pivotal work in developing 193 nanometer lithography, which had a huge national impact and really underpinned some of the semiconductor fabrication across the world over the past couple of decades. And then I think a nice example of some of the system prototyping that we do is in the bottom right. It's back in, I think, 2013, 2014 timescale, we demonstrated a laser comm free space link to the moon, which at the time was the longest laser comm link ever made. One of the things I like to point out about this demonstration is it was enabled by very, very sensitive single photon detectors, superconducting detectors, superconducting nanowire detectors, which were made both at Lincoln Laboratory and also on campus with Professor Carborgren. So a really great example of how those ties run deep and are enabling in terms of MIT having a national security impact. So quantum at MIT Lincoln Laboratory, we have about a 200 or so staff level of effort. I see a number of the Lincoln folks here today. I'll try to make a few call outs, but I know that I'm gonna miss some of you, so I apologize. Our efforts are spread across really 3 different areas. One is quantum computing. I'll talk about that in a second, led by Molly Schwartz and Daniel Braji, who I think are both in the audience. And John Owen Yoder is also very involved, Kyle Cerniak. The second area is quantum interconnects and quantum communication, distributing quantum states and quantum information. Scott Hamilton, Ben Dixon, I see you over there. So I want to call you out. And then what we think is really the most near-term area for realizing the field impact of quantum technologies is in quantum sensing. That effort led by Daniel Braji, and I'll tell you just a little bit more about that in 1 second. So just to dig a little bit deeper into some of those areas, we're working on enabling 2 different quantum computing platforms at MIT Lincoln Laboratory. The first is a superconducting platform based on aluminum metal. This is devices that are built in our 8-inch wafer fabrication, 90 nanometer node silicon foundry, which is out at Lincoln Laboratory. It's also a secure foundry, which is very important for national security applications. And more recently, so we've been working using that fabrication equipment really over the past 20 years, 25 years, together with folks like Professor Will Oliver, who started off at Lincoln and is now here on campus to develop record-breaking devices and qubits in the superconducting regime. More recently, we've extended that into 3 tiers so that we can make it easier for room temperature readout and control of those types of devices. On the right, we're also working on integrating trapped ion computings into a wafer platform by integrating the ion trapping with integrated photonics, integrated electronic readouts, and also some of those single photon sensitive detectors for reading out some of the quantum states. Some of that work has been done, for example, with Professor Ike Schwang, and John Cheverini is another one of the key Lincoln Laboratory players in that work. So one of the things that we feel is very important is to try to enable the entire national ecosystem in the quantum area. So we have these very sophisticated tools and platforms, and it takes a lot of effort to get them working and working well. And so one of the things that is very important to us is to make those available to the country, to research groups really across the ecosystem in order to enable more rapid development of the area as a whole. So that's something that we've done, making those platforms and those devices available across superconducting, the trapped ion, and also some of our NV Center Diamond work as well. I just want to highlight in the superconducting area, we have an effort called the Squill Foundry effort. We have over 30 research groups across the country which are designing into our process. This is work that was kicked off by the Laboratory for Physical Sciences, their National Quantum Initiative, and really has been an important way that we're helping to float all the boats of the quantum ecosystem across the country. We're also working very hard on how to distribute that quantum information, both for interconnects to, for example, link up multiple quantum computers, but also longer distance communication. We're working across many areas here. I just wanted to highlight the fiber link that we have. We have an actual optical fiber link that's going from our lab, from Scott Hamilton's lab, to campus. To Dirk England's lab, and I think there's also a node in Professor Ike Schwang's lab, and then also to Misha Lukin's lab at Harvard. That's been used to demonstrate record fidelity, quantum state distribution, and storage together as a great Boston area collaborative effort. So super exciting work. And then finally, I did mention that quantum sensing is where we see the potential for the nearest term impact in terms of bringing those technologies out to the field for national security and other types of sensing applications. I just wanted to show you this picture. This is an example of one of the rapid prototyping efforts that we took with a quantum sensor, with a nitrogen vacancy diamond sensor. In this case, this was a vector diamond magnetometer, which was flown in a package below a helicopter. And we use this to demonstrate that if GPS were to be denied, that we could do much better than state-of-the-art inertial navigation system positioning with the vector magnetometer. A lesson learned, be sure that you let the local police know that you're flying something that looks a little bit like a missile around on a helicopter. That's a very important thing to do if you're going to do a field test. So, all of that work is really integral. I think a collaboration is really an understatement here. Integral to all this work are the very close ties between MIT Lincoln Laboratory and MIT campus. I'm just showing you a few pictures of some of the collaborations of Lincoln staff, students, professors. That is really just integral to our success. And one way to think, I think of the partnership is that, MIT, of course, has many, many different pathways toward impact of the technology that we as a community are developing, and many pathways to industry. But I think I'd like you to think of Lincoln Laboratory as one of many amplifiers. I think Will Oliver used the word amplifier before for the Center for Quantum Engineering. But think of Lincoln Laboratory as one of many amplifiers in order to help take some of the technology that's being developed on campus, that's being developed collaboratively with Lincoln Laboratory, apply that to national security applications, and just one more way that we can get that out to having an impact for industry. So really, that's what I wanted to say. We're thrilled to be here. We're thrilled to be a part of this. We know that this initiative is going to expand upon what's an already thriving partnership and collaboration between Lincoln and campus. And we see many, many opportunities to amplify the national security impact, in particular, of QMIT. Thank you very much.